Hi, my name is Rohan Wag. I am 16 years old and I live in Portland, Oregon. I enjoy solving problems, designing, building, and testing my own solutions, learning new things, and of course, science. For my project, I knew I wanted to find a way to combine all of these things I enjoy with my passion, microbial fuel cells. Around 4 years ago, in 7th grade, I started building and designing my own fuel cells. However, I realized that microbial fuel cells are limited in their applications because they're not able to produce enough power to work as an energy source. So I decided to look beyond energy and realized I could use microbial fuel cells as a sensor. More specifically, I wanted to see if I could create a better soil conductivity sensor using microbial fuel cells. But why soil conductivity? Soil conductivity, typically called soil EC, is a measure of soil salinity that is typically used to estimate crop yield, plant sustainability, and nutrient availability in the soil. Keeping a proper soil EC is extremely important for ensuring a proper environment for plant growth. Currently, the methods available for measuring soil conductivity are extremely expensive, time-consuming, or both, leaving the need for an affordable, low-maintenance, and continuous sensor. I decided to design a multi-anode MFC sensor that gets implanted into the ground and gives voltage readings at various depths. Contrary to typical MFCs, which have a 1-to-1 ratio between anodes and cathodes, I decided that since I was not trying to optimize power output, I would not need multiple cathodes in my design. Instead, I had the topmost electrode serve as the cathode for all the anodes in the sensor. One important aspect of my design is that it is modular, to allow the user to change the depth of the sensor to better match the depth of the topsoil at the specific point they're measuring. This allows the user to get the most accuracy, as more depth means being able to fit more modules and getting more data readings per sensor, giving a more accurate overall estimation of the soil EC. Each additional module also adds another anode to the sensor, allowing one of my sensors to hold multiple microbial fuel cells, which allows me to get different voltage readings at different depths into the soil. This means that for each cell in my sensor, I get an independent voltage over time chart at that specific depth, which I then use to calculate the soil EC. The equation for soil EC is the change in the length or the depth of the sample over the change in resistance multiplied by the cross-sectional area. However, since each cell was only going to give me voltage, time, and depth, I needed to find a way to relate the voltage and time measurements into a resistance measurement. I started by looking at Ohm's law. I realized that I had voltage, I needed resistance, but I did not have the current. So I needed to find a way to estimate the current in my microbial fuel cell using my voltage and time measurements. I did some research and found that I could estimate the current for each microbial fuel cell as the charge rate over time, or as the slope of the voltage time chart multiplied by the integral at a point on that chart called the equilibrium point. I then combined this estimation for current with my known average voltage to get an estimation of resistance through Ohm's law. As a result, I now had the estimated resistance of each cell at each of their depths, which is what I needed to calculate my soil EC. For the final calculations, I take the resistance over the depth of each cell in the entire sensor and use it to calculate the resistivity of the soil. The resistivity of the soil is calculated as the slope of the RSD, or resistance over depth, chart multiplied by the cross-sectional area of the electrode. Since the resistivity is the reciprocal of conductivity, I can then find my soil EC by taking my resistivity value and finding its inverse. I then proceeded to test my sensor in 3 different prototypes. For each test, I compared it with a conventional soil EC probe in order to test the accuracy. I was able to get my sensor to measure within plus or minus 4 millisiemens per meter as compared to the probe. In addition, I was able to accurately predict soil EC after over 90 minutes of testing, when compared to a probe measurement at the 9th testing segment, showing that my cell provided accurate soil EC measurements. The data received from an array of my sensors can be plotted on a 2-dimensional bird's-eye view of a field, called a field map. From there, I can calculate the watering needs, estimated crop yield, and soil health over the field and represent it on a 2D scale. Overall, I was able to create an affordable, low maintenance, and continuous soil EC sensor using microbial fuel cells. that can revolutionize the way we farm.